All right, so this is Unit 1, Lesson 4. The lesson is called Inverse Functions. What we're going to learn in this lesson is what is an inverse function, how to tell if a function is an inverse, and how to find the inverse of a function. So a quick technical definition of inverse functions. An inverse function is a function that kind of undoes the action of another function. So if we say that f of x equals y, so if you input x into f, the output is y. G would be the inverse of f only if g takes that output and sends it back to the input. So in other words, g of y would have to equal x. So here's what that looks like as a mapping. So if we have an input x of 1 and f maps 1 to a, the inverse function g would mean that g of x would map a back to 1. Or if f maps 2 to c, then g would map c to 2, and so on. So some notation for writing inverse function notation. We write the function f, and then it's not an exponent, but we write it as if it looks like an exponent. So it'd be f with this superscript of -1 of x. Two ways to say it. We could say the inverse of f of x, or more quickly, we could say f inverse of x. And I'll probably say the two interchangeably. So now, here's an example question. Is g of x an inverse of f of x? And so, let me just fix my mouse pointer here real quick. I went to add. Okay. So if f of x is 2x plus 6, and g of x is 1/2 x minus 3, the question is g of x an inverse of f of x? Or we could write that same question this way with our notation. Is g of x equal to f inverse of x? So we could try some examples, and this doesn't prove anything. We're just kind of playing with some numbers here. But if we use the inputs of 1, 2, and 3, and we use those inputs of f, 1 has an output of 8, 2 has an output of 10, and 3 has an output of 12. So if we look at g, and we take those outputs and put them in the function g, 8 gives us an output of 1, which puts us back to the beginning of the input for f. When f puts 1 in, the output's 8. When g puts 8 in, the output goes back to 1. Similarly, 10, if we use that as our input for g, it sends it to 2, which is our input for f. And 12 in g, the output is 3, which was our input for when the output was 12 in f. So if we look at these three examples, we kind of get the feeling that g of x is in fact an inverse function of f. We haven't proven it yet, but now we can look at this with some confidence and say, yeah, I think g of x is f inverse of x. Just a quick note on that. If g of x is the inverse of f of x, then by definition, f of x would be the inverse of g of x. That works both ways. So now how do you find the inverse of a function? So if I know f of x equals y, then it stands to reason that f inverse of y equals x, or f inverse will take our output and send it back to the input. So here's how we do that. We can take f of x equals 2x plus 6, our function, and we can write this as an equation. In other words, we change f of x out and put y in its place. So this now reads y equals 2x plus 6. And if we're swapping the input and the output around, then in our equation, we're going to move x and y to where each other are. So instead of y equals 2x plus 6, it's going to be x equals 2y plus 6. We're just swapping the x and the y around. And then from there, we're just going to solve for x. First thing I'm going to do to solve, we're going to solve for y. The first thing to solve for y is we're going to subtract 6 from both sides. So we have x minus 6 equals 2y. And then to get y by itself, we're going to divide both sides by 2. On the left, we're going to divide each term by 2. On the right, we're going to end up with y. And if we simplify that, we find we get 1/2 x minus 3 equals y. And so now we can take y out and replace it with f inverse of x and say f inverse of x equals 1/2 x minus 3. And we can see that that inverse function is the same as the g of x from the previous slide. The only difference between this method and plugging in values is now we've actually proven and we've shown that g of x is in fact the inverse of f. Whereas before we were just kind of playing with numbers and guessing at it and trying to get some intuition. Now we've proven it. Let's look at some examples. So if we're going to graph the inverse function, the red line here represents f of x. How we're going to do this is we're going to look at the line and we're going to figure out some mappings for f of x first. So if I look at -6 as an input for f of x, -6 on the x-axis is going to map to +1. So if f maps -6 to +1, then f inverse is going to take that +1 and send it back to -6. So that means the point 1, -6 is a point on our inverse graph. So 1, -6 is right here. That's 1 point. We can repeat that process to find more points. -3 is an input for f, gives us an x value, gives us a y value of 0, which means -3 is mapped to 0 with the function f. So f inverse is going to take 0 and send it back to -3. So 0, -3 is a point on our inverse graph. 0, -3 is right here. And we can continue this process. We will see that we have 3 more points we can get. Basically what we're doing is every point, every ordered pair on the original graph, we just take the x and the y value and we flip them around. X becomes y, y becomes x, and we get these new set of points. And so now we have this green line that maps f inverse of x. One more thing to note, what is this blue line here? This blue line is the line y equals x, and it represents the a line of symmetry between the original function and its inverse function. So if I rotate my function over, or if I reflect my function over this line of symmetry, then I will end up with the inverse function. In other words, if this is a piece of paper and I folded it on the blue dashed line, when I fold it in half, this right side of the red line would perfectly meet up with the left side of this green line, and the left side of this red line would match up perfectly with the right side of this green line. It's symmetrical. All right, one more example. So here's a parabola. If I do the same process here, we'll get a similar result. We'll find the inverse function. So I know that if I look at the input value of x equals 0, f is going to map 0 to +7. There it is. Which means f inverse is going to take +7 and map it back to 0. So 7, 0 is a point on our graph, and here it is right here, 7, 0. 1 maps to 4 on our function. 1 goes to 4. So on our inverse function, 4 is going to map to 1. So 4, 1 is a point on our inverse graph. 2 gets mapped to 1 in f of x. So since 2 goes to 1 in f, 1 in our inverse function is going to go back to 2. So 1, 2, here's that point right there. And now if we keep going, 3, 0 is a point. 3 goes to 0, which means 0 goes to 3 in our inverse function. 0, 3 is right here. And then after that, we're going to hit the top of the parabola, and we're going to start moving back to the right. And when we do this next point here, we should notice 4 maps to 1, which means in our inverse function, 1 is going to map to 4. 1, 4 is right here. And we've hit a point right here where we've realized something. And I'm not going to spoil it yet. If you haven't realized something about our inverse function yet, take a moment, take a look at it. If we look at our mapping, we can see that 1 is going to map to 2, but also to 4. So we know that in this case, f inverse is not actually a function. It's just a relation. So what that means is uh, our original function f is actually a function, but its inverse is not a function because we have numbers here, 1 that maps to 2 different numbers. If we continue this graph, we'll see that 4 also maps to 2 different numbers and 7 maps to 2 different numbers. We can confirm that looking at our graphical representation of our inverse function. It fails the vertical line test, as in I could draw a vertical line that'll hit this parabola more than once. Again, we'll notice the blue line, y equals x. This again, for any graph, this will be true. Y equals x represents the line of symmetry. We can reflect our original function, the red line, over this line of symmetry, and it'll map perfectly to the green line, the inverse function. All right, how about when we're looking at equations? So as we said before, if I want to find the inverse function, all I have to do is write this out in terms of y and x, and then swap the y and the x around. So f of x is ultimately going to become x, and x is going to become y, and then we're going to solve for y. In this particular problem, that means we subtract 9 from both sides, and then we divide both sides by negative 1/3, or we multiply both sides by negative 3. Same thing. And that'll yield us an answer of negative 3x plus 27 equals y. So our inverse function here is f of inverse of x is negative 3x plus 27. A similar example over here, again we swap x and y around, and then we can solve for our new y. So add 10 to both sides and divide both sides by 2. We get an answer 1/2 x plus 5 as our inverse function. And you could write that one of two ways. You could write 1/2 x, so 1/2 is the coefficient for x, or you could write it as a fraction x over 2 plus 5. Same thing. A couple more examples. Writing our inverse function, we're going to write x equals 3y to the power of 5 plus 1. So x becomes y, h of x becomes x. When we solve for y, we'll subtract 1 from each side, divide each side by 3, and we'll get y to the power of 5. So to get rid of a power of 5, we take the fifth root of both sides. And so we have this 1/3 x minus 1/3. We take the fifth root of that. First might look a little intimidating, but don't forget we're not actually trying to evaluate x. So it's okay that this thing looks nasty with fractions and radical signs, because our inverse function, we're just going to leave it like that. Fifth root of 1/3 x minus 1/3. And we're going to call it done. J of x we can simplify with the same process. In this case, our process is going to be multiplying both sides by 5 and then adding 2 to both sides. Two more examples. For k of x, we swap the x and the y. Divide both sides by 7 first, and then we're going to add 1 to both sides. P of x, swap x and y, divide both sides by 5. And we have the third root of x, the third root of y. So what we're going to do to get the y by itself is we're going to take both sides of the equation and take them to the power of 3. Power of 3 and third root are inverse operations, so they'll cancel each other out. We'll be left with 1/5 x to the power of 3. We're going to distribute this power of 3 to both bases. So 1/5 to the power of 3 is 1/5 times 1/5 times 1/5, or 1 over 125, and then x to the power of 3. So we can write the inverse function here as 1/125 x to the power of 3, or x to the power of 3 over 125. So our takeaways for this lesson, we now know how to read this symbol right here. This means inverse of f. We understand inverse as taking outputs and inputs and switching the order. So our outputs are now our inputs, and our inputs are now our outputs of our original function. Or in other words, it undoes the operation that f would do. We now know that we can find the inverse of a function just by swapping the x and the y out. And that works for pretty much any equation we can write. And we also learned that a function's inverse isn't always a function.